Okay, so improper integrals. So we will discuss the improper integral today. Okay, we have seen already the Riemann integral. When the function f be a bounded function over the closed interval ab, and if the lower Riemann integral a bar f dx and b bar upper Riemann integral, when both exist and coincide, then this be denoted by a to b f dx, and is called the, we say f is Riemann integral function over the interval ab. So for a bounded function, the Riemann integral of a function fx which is bounded over a closed interval can be defined, provided this limit exists. The idea of extending this limit, why we consider only a to b, it may be a to infinity or minus infinity to b, or maybe minus infinity to infinity. So this idea of extending the integration, the range of the integration, is done by Cauchy, and he has introduced the infinite integrals by taking the range of the integration infinite, range of integration infinite, and second be the function is unbounded in the range, because here in Riemann integration we consider f to be bounded and the range of integration is taken to be finite. But what the Cauchy extended this concept of Riemann integration by choosing the range of the integration finite, or the range of the, or maybe both, or both function is unbounded in the range. So by this way he has introduced the concept of infinite integrals. So Cauchy has introduced the concept of infinite, or we also call it a improper integrals. Okay, the first one, when the range of integration is finite, in the case 1, that is when range of integration is infinite, when the range of integration is infinite, then the integrals are known as then infinite integrals are known as improper integral of first kind. And in the second case, in case 2, that is the range of the integration, that is the function is unbounded in the range, that is between a to b, the function have a point of discontinuity at the point either a or at the point b, or maybe in somewhere inside c. So function becomes unbounded, a discontinuity of the first kind, it becomes unbounded at either in the lower limit or maybe upper limit, or maybe any point in between this. So if the function is unbounded in the range, then the infinite integrals are known as improper integral of improper integral of second kind. And third case when both may be mixed up. So it is a mixed type of improper integral will also be there. Okay. So we will take up this. We define the improper integral of the first kind and second kind as follows. First improper integral of first kind. Let us suppose fx be bounded and integrable in every interval ax where x is greater than a. Then we define integral a to infinity fx dx as limit of this a to x fx ft dt, you can say ft dt when x tends to infinity. That is, when x tends to plus infinity, then this plus infinity, then we get. Now, because this integral a to x ft dt exists, because the function f is bounded and integrable in every interval a to x, it means integral a to x ft dt, this Riemann integral will exist for each x which is greater than a. So the limiting behavior of this integral when x tends to infinity, if this limit exists and comes out to be a finite quantity, then we say a to infinity fx dx, this improper integral of first kind exists. So then this improper integral exists. If this exists, then we say the improper integral a to infinity fx dx exists or converges. Okay. If this limit does not exist, we say diverges. If this limit does not exist, then we say the improper integral a to infinity fx dx diverges. Okay. Either it comes to be infinity or maybe the limit does not exist, we say it is diverges. In a similarly, we define integral minus infinity to a fx dx as limit x tends to minus infinity, say x to a ft dt, where the x is always less than a, and assume that this integral will always is well defined and exist. So if this limit exists, then we say this integral converges. If the limit does not exist, we say the integral diverges. The third case may be we also have the integral minus infinity to infinity fx dx, and it is defined as the integral minus infinity to a fx dx plus integral a to infinity fx dx, and if both the integrals exist, if both the integrals on the right hand side exist, then the integral minus infinity to infinity fx dx will exist. If any one of the does not exist, if any one of them, any one of the right hand side integral does not exist, then the improper integral minus infinity to infinity fx dx will not exist, or we can say will not converge. Okay, that is diverging. The value, this is one, the value of the integral one, the value of integral minus infinity to infinity fx dx with the help of equation 1 is known as the general value, is known as the general value, while the value integral minus infinity to infinity fx dx, which can also be written as limit minus x to x when x tends to infinity ft dt. This will also give minus infinity to infinity. The value of this, while the value of this integral calculated with the help of this is known as the principal value, is known as the principal value of the integral, principal value. Okay. Now, as you know, the principal value, it is seen the principal value of an integral may exist even then the general value does not exist. But in case the general value exists, then is equal to the principal value, then it is equal to the principal value. So, what we have seen is that improper integral of the first kind can be written in three ways, three types of way, either a to infinity or minus infinity to a, or maybe minus infinity to infinity. In first two cases, just to test whether it is limit integral exists or not, consider the a to x ft dt as if it is a definite integral, find out the value, get the terms of x in terms of x, and then let x tends to plus infinity. If this limit exists, then we say this integral has a value equal to the value of this limit, and we say the integral converges. If limit does not exist, okay, or it goes to infinity, then we say this integral diverges. The same case happens with the second case when minus infinity to a and so on. So these two are different cases, is clear cut, convergence or divergence will come. In the third case, minus infinity to infinity fx dx, as this can be written in two ways. One is minus infinity to a fx and then a to infinity, when one of the limit is infinity or minus infinity, another limit is finite. So these two integrals in the right hand side, they are basically the improper integrals of the kind 1. then the existence of this integral will depend on the limiting value of this first as well as the earlier one. So if both the limit exist, if both the integral exist, then only we say this improper integral minus infinity to infinity fx dx will exist. If any one of the limit does not exist, then this improper integral will not exist. Now since the same integral we can also put it in the form of minus x to x ft dt, that when x tends to infinity it also gives the minus infinity. So what's the difference between these two? This is the first, this is second. First is this, the way in which written, and second one is this. So if the limit of the first exists, if the integral where the both the limit exists, then limit of the second will definitely exist and equal to the value of the integral. But if the second exists, then first may or may not exist. So that's what he says, the principal value may exist, even the general value does not exist. Now let's see, for example, suppose I wanted to take this integral minus infinity to infinity x dx. Okay. Now let us look. This can be written as minus infinity to a x dx plus a to infinity x dx. Now both the integrals, when you find x square by 2, and then this can be written as limit t tends to minus infinity t to a x dx plus limit u tends to minus infinity u tends to plus infinity a to u x dx. Now if I calculate it, what you get? X square by 2, so t square by 2, and then sorry, x square by 2 and t to a, and limit x tends to t tends to minus infinity. So this will be this, and then second one is x square by 2 under the limit a to u and limit u tends to plus infinity. So obviously it will go to infinity. So limit this value does not exist. So the integral diverges. However, if I take the principal value, however, if we take minus infinity to infinity x dx as integral minus t to t x dx limit t tends to infinity, then what you get? This you are getting x is t square by 2 minus t square by 2, is it not? X square by 2, and then limit lower and upper limit t tends to infinity, and that comes out to be 0. So what says the principal value of this integral exist and equal to and is equal to 0. However, the general value does not exist. So this verifies our claim that though the principal value sometime may exist, but general value may not. Okay. Now let's take some few examples. We are say we claim this this example will also be used as a standard results to compare the function to be tested. Okay. So first is that integral a to infinity x to the power minus n dx, where a is greater than 0. We claim that this integral is convergent for n greater than 1 and divergent for n less than or equal to 1. Okay. So let's see the proof. Solution: a to infinity x to the power minus n dx. This can be written as limit x tends to minus n dx a to t tends to infinity. So, this will be equal to x to the power minus n plus 1 over minus n plus 1, and then divide integral limit a to t and t tends to infinity. Okay. So, that will come out to be 1 over 1 minus n t to the power 1 minus n minus a to the power 1 minus n, and limit h t tends to infinity. So, case 1, if our n is greater than 1, then in that case n is greater than 1, then this 1 minus n becomes negative. So, it will come in the denominator. So, when t tends to infinity, it will go to 0. So, only left out is minus of this. It means the value will come out to be a to the power 1 minus n over n minus 1. That will be the value. So, it is nothing but a finite value, a finite. So, it is convergent. Now, on the other hand, if I take n to be strictly less than 1, then this is positive. So, it will go to infinity. So, value will go to infinity, therefore, it diverges. And what about for the n is equal to 1? When we take n is equal to 1, for n is equal to 1, the integral reduces to a to infinity 1 by x dx, and that is nothing but log of x. Log x means log x, and then limit a to t and t tends to infinity. So, this will diverge. So, the result follows that x to the power 1 upon x to the power n is convergent when n is greater than 1, diverges when n is less than or equal to 1. So, this can be treated as a standard result. Then another example which we can also use as the standard result, but prior to this, let us come to definition for improper integral of second kind. Okay. Now, what we have told that in this second kind, the limit of integration or the range of integration is finite, a to b, but the function need not be a bound, it will not be a bounded function in fact, because if it is bounded, range is finite, then one can introduce the one can say the Riemann integral of this function will exist, provided the lower and upper limit is exist and are identical. Okay, but the function is not bounded and it has a point of discontinuity, it has a sudden jump, it goes to plus infinity or minus infinity, then function cannot be, we cannot say a to b fx dx a Riemann integral function, because the condition is function must be a bounded function. So, in such a case we get the concept of the improper integral of second kind. Okay. So, let us assume let fx be unbounded in the closed interval say a b, but bounded n integrable in every interval a to x, where x is strictly less than b. So, the function is like this is our a b. So, so far we take any point x, the function is bounded, but as soon as it reaches to b, it is unbounded, it goes to infinity all of a sudden. So, what we say this, then we if limit of this, if a to x tends to, if limit of this a to t fx dx when t tends to b, uh, say here b minus 0 from the negative side, means from the left hand side I am approaching, b minus 0. If this limit exists, then we say the improper integral a to b fx dx, this limit converges, otherwise diverges. Okay. So that is what. So here b is the only point of infinite discontinuity of fx. Okay. So what we do is, in that case, we basically write thus. In this case, thus we have here a to b fx dx. This we can write as the limit epsilon tends to 0, and then a to b minus epsilon fx dx. Now up to b minus epsilon, this function fx is bounded and integrable. So the value of this can be obtained, but it depends on epsilon. So as soon as you take epsilon tends to 0, it means we are approaching the b from the right hand side. This is b minus epsilon. So when epsilon tends to 0, we are approaching to b from the left hand side towards this. So when we are approaching, if this limit exists, then we say this integral exists and convergent, otherwise it will diverge. Now similarly, if a is the only point, if a is the only point of discontinuity, only point of infinite discontinuity, means the function is unbounded at this point. Infinite discontinuity of the function fx, in the interval ab, then we have integral a to b fx dx is the limit x tends to a plus epsilon, integral x to b a plus epsilon, so x to b ft dt, and this is the same as limit epsilon tends to 0, integral a plus epsilon to b fx dx. So if this limit exists, then integral a to b fx dx will be convergent, is convergent, otherwise it will diverge. Okay. The third case, if the function fx is unbounded, in an arbitrary small neighborhood, in an arbitrary small neighborhood of the point C, which lies in between A and B, then we define the improper integral of the second kind as a to b fx dx as the limit of this sum of the two integral a to c minus epsilon tends to 0 fx dx plus limit epsilon tends to 0 integral c plus epsilon to b and then fx dx. In fact, this should be epsilon dash, so that you are not getting the same epsilon. Okay. Now, if both these integrals exist, if both integrals on the right hand side exist, then integral a to b fx dx will exist and is said to be convergent. And its value is known as the general value, while the same thing, the principal value, in this case principal value, the principal value may of the integral is defined to be limit epsilon tends to 0 integral a to c minus epsilon fx dx plus integral c plus epsilon b fx dx, and is denoted by is denoted and is denoted by the principal value of this integral a to b fx dx, which has a discontinuity at a point c, infinite discontinuity at a point c. Now again, this limit, this is say 3 and 4, and this one is say suppose 3. Again the same case as in earlier, the general value, if it exists, the principal value has to exist. But if the principal value exists, the general value may or may not exist. Okay. For example, if suppose I take this integral minus 1 to 1 by x dx. Now this integral, the limit of integration is finite, but the function is not defined at x equal to 0. So it is an improper integral of the kind 2. Therefore, we can calculate this value of the integral as minus 1 to say epsilon 0 minus epsilon, is it not, 1 by x dx plus 0 plus epsilon dash and 1 by x dx to 1. And when you compute this value, what happens, this is log x, and log of x at the point 1 is 0, but when epsilon you take, epsilon tends to 0, it goes to infinity minus infinity, so this tends to infinity, the diverges. Limit does not exist. But if we take the principal value of this integral 1 by x dx, this is the same as the limit epsilon tends to 0 minus 1 to 0 minus epsilon 1 by x dx plus 0 plus epsilon 1 by x dx to 1. What we get, the value will come out to be 0. Just integrate it, substitute, get the answer. Okay. So this value will come. So principal value will be there. Now in case if note, if the function is unbounded, if the function fx is unbounded at both ends of the interval ab, both ends of the interval ab, or at a finite number of points, in the interval ab, then we can divide the interval into finite number of subintervals in each of which fx is unbounded at the end, at one end only. And if the integral exists, in each of these interval, these, in each of these intervals, in each of these sub intervals, then the integral a to b fx dx exists, otherwise not. Okay. So, that is what is the meaning of this is, suppose we are having this interval a b and the function is such which has a point of discontinuity at these points, finite number of points. These are the points of infinite discontinuity. It means the function is unbounded at this point, discontinuity, okay, at this point, including the point a and b also. So, what we do is we divide this into the intervals. So, we take the sub intervals like this. Suppose at this point, then we can take this interval where the function is only discontinuous at this point, or maybe at this point also, then we can say a minus epsilon and then some point between we can find out, so that at only one point it has a point of discontinuity. Okay. Similarly, in this interval only at this point is in point of in discontinuity and like. So, over these sub intervals we can find out the value of these integrals and take the limit. If all these limit exist, that is the right hand side integral exists, then left hand side integral will exist, and we say this integral converges, otherwise not. Okay. For example, if suppose I take the interval say 1 over x into x minus 1 dx, suppose I take this integral. So, 0 and 1 are the 2 points. Okay. So, I am taking 1 and 2, this integral is I am taking. So, obviously at the point 0 the function is not defined, it goes to infinity, x equal to 1 also the function is not defined. So, what we will break up into 0 to 1 plus 0 to 2. Okay. So, what 0 to 2 at the point 1 is there, so we can change it 1 and then 1 to 2. Okay. So, what happen is here we take the minus epsilon, here we take the plus epsilon, and in that case 0 minus epsilon and then epsilon tends to 0. So, this is the same as minus 1 to 0 minus epsilon, limit epsilon tends to 0 plus limit epsilon dash tends to 0, 0 to 1 minus epsilon, and then limit epsilon double dash tends to 0, 1 plus epsilon double dash to 2, and thus see the value. If the integral exists all the three, then this integral will exist, otherwise not. So, this is what we get. Okay. Now, again as I showed, there are few examples further which are treated as an standard results and can be used to compare the unknown integral with these known functions, so that one can identify whether the given improper integral converges or diverges. Okay. So, let us take one example here. We claim that this integral 0 to a x to the power minus n dx is convergent for n is less than 1 and divergent for n is greater than or equal to 1. Now, if you see this example and the previous examples which we have seen, earlier the example was a to infinity x to the power minus n. So, here because of the upper limit was infinity, the integral becomes improper, and that is called the improper integral of the first kind, and in that case the result was when n is greater than 1 series converge, this integral converges, when n is less than equal to 1 diverges. But here the point of discontinuity is 0. So, the result is something different, means do not confuse with that. This is at the point 0 the function becomes unbounded. So, the result said when n is less than 1 it is convergent, greater than 1 divergent. Or we can also write like this: if suppose we have integral a to b 1 over x minus a to the power n dx, then this integral converges if n is strictly less than 1, diverges if n is greater than equal to 1. So, this clearly shows that x equal to a, the function becomes unbounded. Okay. So, let us see the way we will prove this, and this is just the generalization. When you substitute a equal to 0, you get this result, okay, like this. So, let us see the solution for it. So, what we do is we start with the 0 to a x to the power minus n dx, and this can be written as what? Limit epsilon tends to 0, epsilon to a x minus n dx. If this integral exists, then this integral will exist convergent. Okay. So, that value will come out to be what? A 1 minus n minus epsilon 1 minus n divided by 1 minus n, where n is not equal to 1. Okay. So, this limit will tends to the a 1 minus n over 1 minus n when n is less than 1, because n is less than 1, this becomes positive. So, epsilon tends to 0 means it will go to 0 and we get this value, but when n is strictly greater than 1, this is negative. So, 1 by epsilon will go to infinity. So, it will go to infinity, diverges. And for n is equal to 1, again this integral reduced to 1 epsilon by a 1 by x dx, epsilon tends to 0, that is equal to log x, and then epsilon to a, epsilon tends to 0 will go to infinity. So, diverges. So, this proves the results for it. Okay. The second example again, say suppose I take this integral 0 to infinity x to the power n minus 1 over 1 plus x dx, when this integral when n is less than 1 is convergent, is convergent if n is greater than 0. It means this integral converges for all n, that is the integral I converges if n lies between 0 and 1. Okay. Now, if we look this integral, this is a mixed type of integral. Mixed type means limit of the integration is infinity. So, it is an improper integral of the first kind, but the function itself x to the power n minus 1, when n is less than 1, this x will come in the denominator. So, when around the point 0 or x tends to 0, the function is undefined. Therefore, it is also an improper integral of the second kind. So, this integral is a mixed type integral, which is improper integral first and second kind. So, in order to judge the convergence part of this integral, we will break up a two integral first. In the first case, when the function becomes unbounded at 0, another case when function is bounded, but at the point infinity only we have to test the convergence part. So, what we do is we consider the integral I, which is integral 0 to infinity x to the power n minus 1 over 1 plus x dx. This we can break up into two parts, 0 to 1 x n minus 1 1 plus x dx plus integral 1 to infinity x to the power n minus 1 1 plus x dx. Let it be first and second. Okay. So, first and second. So, first integral has a point of discontinuity unbounded at the 0, while the second integral is for 1 to x, it is finite bounded, but at infinity its problem is there. So, let us test with so consider say I1 and then I2. Okay. So, consider I1. I1 is 0 to 1 x to the power n minus 1 over 1 plus x dx. Now, what happened? This 1 plus x is not going to affect the whole integral. This becomes improper because of this term x to the power n minus 1, and n is strictly less than 1. Therefore, for this integral, we have to test it with our previous knowledge. What this knowledge is, we have seen, we know that integral 0 to 1 x to the power minus n dx converges if n is x tends to a, if converges if the n is less than 1, is it not? If n is strictly less than 1. Okay. So what we say this this integral is convergent when n is strictly less than 1. Okay. So here this is nothing but what, n minus 1. So I1 converges if minus times of this is strictly less than 1, but this minus time implies n is greater than 0. So this is the part for convergence. Second one is second I1, this integral 1 to infinity x to the power n minus 1, 1 plus x dx. So again this integral converges when this is greater than 1, is it not? So this portion, that is x to the power n minus 1, is equivalent to, that is equivalent to, it should be bounded also, is it not? So x, so what we do is 1 to infinity x to the power n minus 2, 1 by x plus 1. So when x tends to infinity, this denominator will not create the problem. Okay, this is 0 and this will be 1 only. Okay, so now you are getting this part. So when 1 to t, it is bounded functions. Okay, like this. So now this integral converges if n minus 2 minus times of n minus 2, that is minus x to the power n, is greater than 1, that is n is less than 1. So by the previous examples, you can say by previous example, and this is also by previous example. Okay, so that will be so. So this implies the I converges when if n lying between 0, and that is also considered to be a standard result for it. Okay. Now so far we have discussed the many problems, improper integral first kind and their convergence part. But always what we did it, we have computed the value of the right hand side by choosing f signer, and then f signer tends to 0 or f signer tends to plus 0 or something. Then if the right hand side has a finite value, then we say the integral converges. But if the limit does not exist, then it diverges. Now it may not be always be possible, or may be very difficult to compute always the integral and then taking the limit when f sign tends to 0 or maybe t tends to infinity. So to avoid this thing, we have developed certain results or formulae which are helpful in in identifying whether the given improper integral converges or diverges, just by looking the integral and the standard results which we have already shown. These 4 examples which we have discussed, basically I told these will be the backbone, these will be used as a standard results. So we can easily compare with a given integral with our this one of the example, and then we say whether the given integral converges or diverges. Okay, but for this there is certain necessary insufficient condition, just like in a series we have a necessary insufficient condition that series must be Cauchy. When the series is convergent, it has to be a Cauchy sequence, and vice versa for the real and complex sequence, is it not? So similarly here also we have certain results, and that necessary and sufficient condition we just discuss without proof. So convergence of infinite integral. Integrals or improper integral. This is our improper integrals. Okay. So this is what we on the general principle, necessary and sufficient condition. Necessary and sufficient condition. Conditions. Okay. So what we say, for the existence a necessary and sufficient condition for the existence of the improper infinite or we say improper also, improper integrals, improper integral a to infinity fx dx, where fx is bounded, fx is bounded and integrable, bounded and integrable over any finite interval, over any finite interval, say ax, over any finite interval ax, is that corresponding to a given epsilon, corresponding to a given epsilon, a value xi can be found such that corresponding a given fund such that modulus of integral xi to xi dash f of x dx mod of this is less than epsilon for all values of xi dash greater than xi. Okay, so this is one. Similarly, we can go for this second kind. This is the improper integral of the first kind. Similarly, for the second kind, we say when the function fx is unbounded, at a point say b, the necessary and sufficient condition for the improper integral a to b fx dx to be convergent is that corresponding to given epsilon, to a given epsilon greater than 0, of course, a value epsilon dash can be found such that modulus of integral b minus epsilon to this, or b minus epsilon to b plus epsilon, b minus epsilon dash, sorry, b minus epsilon dash fx dx is less than epsilon for all epsilon dash greater less than epsilon, all epsilon less than. So these two statements will be used as a general results, and when you define others, why we get just we define the function one absolute convergence, and then we will stop it. Absolute convergence of the improper integral means the infinite integral a to infinity fx dx is said to be absolutely convergent, absolutely convergent when the integral a to infinity mod of fx dx converges. So that's okay. So remark note is absolutely convergence improper integral will imply the convergence of improper integral. If a improper integral is absolutely convergent, it will converge, and that's all. Thank you very much. Converse is not true. Okay, thanks.